We have our final speaker is Austin. Thank you.
Great. Thank you, Jamie. Good afternoon, everyone. So I'd like to start by putting things in global context for a second, and outline for all of you why I think that studying aging and aging-related biomarkers is probably one of the most effective approaches we can take for preventative medicine. And this is because if we look at the global population above 70 years old, 9 out of 10 of the top 10 causes of death are all age-related chronic diseases. So this opens up an opportunity for us, because if we can identify and then quantify the aging biology that's common across all of these major killers, then we'll be able to develop tools and approaches that allow us to detect, to predict, and also monitor multiple different aging-related chronic diseases all simultaneously. So today I'd like to describe for some of you all the work that we've been doing developing proteomic age clocks based on plasma proteomics data from several human biobanks, and to outline some of the principles that we've been trying to follow to develop these as effective tools for preventative medicine. So I'll start with possibly the most important point, is that we need to develop models and biomarkers that work for everybody. There's already been some discussion of this. There's a scientific imperative for this. We need to have reproducibility. There's an ethical imperative for this. We need to be able to avoid inadvertently contributing to existing health inequalities. And these together allow us to make good on the promise of being able to use precision and personalized approaches for preventative medicine. So a couple of months ago, we published a paper in Nature Medicine describing the development of a proteomic age clock using about 3,000 proteins in 45,000 participants from the UK Biobank. But we built in reproducibility into our process for this. And so we developed our models to make sure that they would validate in different global populations. In this case, we validated these models both in 4,000 participants from the China Kadoorie Biobank in China, also in 2,000 participants from a Finnish cohort in Finland called FinGen. And you can see here the accuracy of the proteomic age clock model we developed. On the left side here, you can see the results in the UK Biobank, but importantly, we showed that the accuracy both in the China Kadoorie Biobank in the center and also the FinGen participants in the middle all show similar accuracy to the models that we built in the UK. And this is despite the fact that the Chinese and the Finnish participants are, of course, a different genetic ancestry from those in the UK, also very different age profiles, but also importantly, different morbidity profiles from the training population. So especially in the case of FinGen, these are all who have had, all the participants for whom we have proteomic samples so far, these are healthy controls, so very little mortality or disease in that population. And of course, the phenotype that we pull out from this proteomic age clocks is this proteomic age gap phenotype, which is just the difference in years between protein predicted age and calendar age. We also showed that this proteomic age gap phenotype has a very similar distribution across different population groups, so across different sexes in all 3 cohorts that we studied, across self-report race ethnicity in the UK Biobank, and also across different geographic regions in China. Okay, so the next principle that we've been thinking about for developing these models is the simpler the better. And the reason for this is pretty straightforward. If we can reduce complexity on the model, we can reduce complexity in the assay we need to look at it, and that will translate to reduced cost for being able to measure these biomarkers where we need to. In our case, what we ended up finding is that starting from 3,000 proteins, you don't actually need thousands of proteins to measure aging. We went from 3,000 proteins all the way down here on the left to 200 proteins with virtually no drop in accuracy in terms of predicting age in the UK Biobank, for example. But even more interestingly, we can go all the way down to just 20 proteins here all the way on the right and still have about 95% of the overall accuracy of these more complex models in terms of increasing numbers of proteins. So then, of course, if we're talking about preventative medicine, we need to make sure that the models and the biomarkers we're using can predict future risk of diseases and frailty, but importantly, in those who don't yet have any onset of those conditions. And this is something that we see in our work here. So what you're seeing here are the associations between this proteomic age gap phenotype built both from the 200 protein models and the 20 protein models in relationship to, on the top here, telomere length and different biological mechanisms related to disease and organ function. And then on the bottom here, also various different measures of functional health and in terms of physiological and cognitive function. And what you can see here is this proteomic age gap phenotype from both the types of models are associated with virtually all of the different functional and biological measures that we look at, both on the left here in terms of the full sample we look at, but then also importantly on the right here in the subset of participants who have no lifetime diagnoses of any major conditions. So what this tells us here is that this proteomic age clock model is able to pick up these changes and declines in functional status in the years and time before the actual onset of any major conditions. We also showed that this proteomic age clock, again, built on both the 200 protein and just the 20 protein models, are associated with future risks, so incidence of mortality, and 18 different chronic diseases. You can see the hazard ratios for all the associations here and the counts of the number of events we have. These are hazard ratios per 1 year of proteomic age gap. So to put this in context for you, if you take people at the top and the bottom of the distribution, it's a nearly 6-fold increase in risk for Alzheimer's disease, for example. We also showed that this proteomic age gap phenotype is able to stratify really nicely different participants into different age-specific trajectories of future disease, and also in terms of mortality. And interestingly, not only can we identify through this very high-risk individuals, but we can also identify very low-risk individuals. So for example, if you look at dementia and Alzheimer's disease, those who are and we look at those who are in the bottom 10% of this distribution of the proteomic age gap, even among people who are 65 years old at baseline, if you look in the next 10 to 15 years of follow-up, less than 1% of them will develop Alzheimer's disease or any all-cause dementia. And we see also in the China Kadoorie Biobank that we're similarly able to stratify participants in terms of future risk for all of the chronic conditions where we have enough cases in that cohort. It's a smaller sample size. And of course, we didn't carry this out in the FinGen cohort because, like I said, those were all mostly, for the time being, healthy participants. Okay, so the next sort of area of work that we've been trying to do to improve our understanding of some of these proteomic biomarkers is to use genetic information to improve our confidence in what we're measuring and improve our confidence in the connections between these proteomic markers and the different health outcomes that we care about. The reason why we're doing this is pretty straightforward. In the arena of drug development and discovery, it's been shown that drug mechanisms with genetic support are nearly 3 times more likely to successfully pass through clinical trials and receive approval. And so I'd argue that we need to be thinking similarly about using this strategy of success for clinical biomarkers of aging as well, and to leverage human genetic data to allow us to understand more the biological connections between the aging biomarkers that we're discovering and the different phenotypes and outcomes that we care about looking at them in relationship to. So in the context of our work, I'll show you a quick example of some of the ways that we've been connecting this proteomic age clock phenotype to the genetics of lifespan and longevity. We carried out a genome-wide association study for this proteomic age gap phenotype in the UK Biobank. And if we compare the GWAS summary statistics from this proteomic aging GWAS with the largest GWAS of longevity that was conducted to date, there's an extremely strong correlation between the genetic architecture of those two traits. Of course, we can also use the GWAS results that we developed in the UK Biobank to then create polygenic risk scores for this accelerated proteomic aging phenotype in other populations. So we did that in the FinGen cohort in about 520,000 participants using the GWAS results from the UK Biobank. And interestingly, what we found is that just using the genetics and the polygenic risk for this proteomic aging phenotype, if you take those who are in the top quintile of this distribution of a polygenic risk for proteomic aging, then that's associated with a 31% increase of living to at least 95 years old. And that's just among the participants in FinGen who have died during follow-up. There's about 60,000 of them. So the last thing we've been doing is actually using exposomics approaches to look and explore and find different types of exposures and environmental interventions, behavior, lifestyle changes that are associated with both the proteomic aging biomarkers that we've been developing, but also more broadly at their associations with aging-related multimorbidity. So we have a paper that's coming out, will be in Nature Medicine in the near future, where we conducted an exposome-wide analysis of mortality and aging in the full UK Biobank cohort. So this is about 500,000 participants. The nice thing about taking this approach is we can look at a few hundred different types of exposome factors in terms of lifestyle, behavior, things in your physical environment, and we can put them all together and analyze them in relationship to premature mortality. And it allows us to comprehensively assess them all together and to prioritize and see and put them into a hierarchy of which are the ones that have the strongest effect and the biggest magnitude of effect on mortality when looking at the full environment together. What we can also do from this is to further sort of narrow down and find the exposures that are not just associated with premature mortality, but then are also associated with multiple other stages in the causal pathway from the environment to the different age-related diseases we care about. So for example, we find the exposures that are not just associated with mortality, but which are associated with our proteomic age clock, are associated with numerous different biological mechanisms related to disease risk and organ function, which are related to intermediate disease risk factors like hypertension, obesity, dyslipidemia, and then of course are associated with incidence of multiple different age-related chronic diseases. And what you see here in the set of environmental factors that we're able to narrow down to is a really beautiful pattern that emerges where you see these exposures that are associated in consistent directions with all of these different layers along the causal pathway from exposure through intermediate biological mechanisms up to the ultimate diseases that we care about. And we think that this is a particularly interesting way where you can narrow in on exposures that are much more likely to be deterministic and drivers of this process because they're associated with the full causal chain and causal pathway. So the other nice thing that I'll mention about most of these exposures is that most of these exposures are also modifiable. So I'll kind of end here, leaving you all with this kind of thought on this final slide, which is that we can really take advantage of the epidemiology and leverage a number of sort of large human population data sets to allow us to not just identify environmental influences that are associated with aging, but to really prioritize and identify some of the interventions and exposures that would be most effective in not just reducing age-related multimorbidity, but as strategies for preventative health as well. So with that, I will end. Thank all of our lovely collaborators all around the world, and thank all of you for listening.
First, we have a good. Do have a couple minutes for questions. Okay, next we have an announcement.
Thank you, Jim.